Welcome back to the Deep Dive, where we take your source material and cut straight to the knowledge you need. Today, we're jumping into AI engineering. This is the field that is, it's basically rewriting the rules of software development right now. And you really know the demand is high when you just look at the compensation.
It's incredible.
Our sources are reporting the median salary for this kind of role is around, what, $242,000 per year?
And that's the median. If you're a senior engineer, maybe at one of the foundational model companies like OpenAI or Anthropic.
We're talking figures of $700,000 or even more.
Yeah.
That level of investment, I think, is the first big clue that this isn't just, a new job title. It's a real fundamental market shift.
It absolutely is. And I think the most important thing for you to get right away is the difference between an AI engineer and, say, a traditional machine learning researcher.
Okay, yeah.
They get confused all the time, but their missions are.
Mm-hmm.
They're completely distinct.
So let's nail that down. What defines that division of labor?
Think of it with a car analogy. The ML researcher. They're focused on inventing a totally new engine. They're the ones deep in the complex math, training models from scratch, focused on algorithmic invention.
So the AI engineer isn't inventing the algorithm itself.
No, not at all. The AI engineer is building the car, the actual robust production-ready application. They take these finished engines, we would call foundation models, from places like Google or Meta, and they specialize in adapting them to solve real-world problems.
That makes so much sense.
The whole job shifts from creating the model to just leveraging and integrating it.
And that distinction, it really clarifies why this field is just exploding right now. The underlying models have gotten so much better, so you can actually solve these high-value problems. And at the same time, the technical barrier for a developer to just start building with them has gotten so much lower.
Exactly. So our mission today is to give you that concise roadmap. We're going to unpack the tech behind these models, explore the key adaptation techniques.
Prompting, RE, agents.
Right. And then detail the practical skills you need to move from writing code to, well, a successful career in AI engineering. Let's start with the engine itself. Foundation models. The whole reason these systems even exist is because of a huge breakthrough in training. Historically, machine learning really struggled with the data labeling bottleneck.
Right, where you needed an army of people to manually categorize millions of images or text snippets. Just super slow and expensive.
Exactly. Foundation models, they largely sidestep that whole problem by using self-supervision.
Okay, so what does that mean in practice?
The model basically learns by predicting masked or missing parts of its own input data. It's kind of like learning a language by reading a book and constantly trying to guess the next word.
And that unlocked the ability to just use the entire internet as training data.
It did. And that's what took us from simple language models to these massive large language models, LLMs, and now even large multimodal models that can handle images and video.
But none of that scaling would have been possible without the big architectural breakthrough, right? The transformer.
Ah, yeah.
What made that so revolutionary?
Well, before the transformer, you had models like recurrent neural networks, or RNNs, and they had to process information sequentially, one step at a time.
So if you asked about a long document,
You had to try and compress the entire meaning of that document into one tiny summary before it could even start to answer. It was slow and, honestly, pretty forgetful.
that sounds like a fundamental limit on how complex things could get.
It was a huge limit. The attention mechanism is what solved that. Instead of summarizing everything, the model can instantly focus on the most relevant parts of the input at any point while it's generating the output.
So it's like being able to instantly reference any page in a 1,000-page book while you're writing a specific sentence.
That's a perfect analogy. And crucially, that mechanism allowed for parallel processing.
So it's not dependent on the previous word being generated first.
Precisely. That's the key. It can process all the input tokens at the same time. That parallelism just made inference exponentially faster, and that's what enabled models to scale up to the size of, a GPT-4.
Speaking of scaling, the research we reviewed brings up some pretty hard physical and data limits to how big these things can actually get.
Yeah, the science around this, the scaling laws, they basically tell us that for the best performance, your training data has to scale up proportionally with your model size.
You can't just make a huge model and feed it a small amount of data.
Exactly not. And this is hitting two really hard limits. The first is training data. We are facing a very real risk of just running out of high-quality, human-generated data on the internet.
So future models might have to train on AI-generated content.
They might, which runs the risk of knowledge degradation. People
Yeah.
call it model collapse. The second limit is simpler, electricity.
Right.
AI data centers already consume a massive amount of power, something like 1 to 2% of global electricity. Continuing to scale is going to demand either massive energy breakthroughs or just totally new, super efficient hardware.
Okay, so that brings us to the AI engineer's toolbox. Because you can't just retrain a $1 billion model for your specific task, adaptation is the name of the game. And we start with the quickest win. Prompt engineering.
Right. Prompt engineering is the art of crafting instructions to get the output you want. It sounds simple, but truly effective prompting requires experimental rigor, lots of testing, versioning. It's a real engineering task.
And a core strategy there is in-context learning, right?
Yeah.
Using examples right inside the prompt itself.
That's right. Whether you use zero shot, which is no examples, or few shot, with a couple of examples, you're always constrained by two things.
The model's context length.
Yep. How much it can hold in its working memory, and
Mhm.
of course, cost. Every single token you add costs money.
So for developers building actual applications, how important is it to stick to the model's specific chat template?
Oh, it is absolutely mission critical. Modern prompts are split into the system prompt. That's where the developer sets the role and the rules, and then the user prompt.
And if you mismatch that format,
Even by adding an extra space or a new line, the model can just completely misinterpret the instruction. You'll get these silent failures where it just ignores your carefully crafted system prompt.
and to get better reasoning, our sources mentioned a pretty simple trick. Just give the model time to think.
Yes, that's chain of thought prompting. You literally just tell the model to think step by step before it gives the final answer.
And that actually works.
It significantly improves reasoning on complex tasks. Or you can use self-critique, where you ask the model to check its own work. The trade-off is always speed and cost, though. More steps means more tokens and higher latency. So when a prompt just isn't enough, we move on to the next tool, which is Retrieval Augmented Generation, or RA.
RAG. This is the essential solution for that knowledge cutoff problem, right? The model only knows data up to, say, 2023.
Exactly. RA lets it access your internal company documents or today's stock prices or real-time data.
So our RAG system has two basic parts.
Two fundamental parts. The retriever, which goes and fetches the relevant external documents, and the generator, which is the foundation model itself. It synthesizes an answer based on that new information.
And that retrieval part is where all the complexity is. What are the main ways to fetch those documents?
There are two main approaches. First is term-based, or lexical search. It's just keyword matching. It's fast, it's cheap, but it only finds documents with the exact words you used.
And
The other is embedding-based, or semantic search. This uses a vector database to understand the meaning of your query.
So if you search for a fast car, it might return results about sports vehicles, even if the word car isn't there.
Precisely. It's much more accurate, but it requires this expensive upfront process to create all those embeddings.
And you can't just feed the model the entire document you find.
No, absolutely not. The data has to be split into intelligent chunks to fit in the context window. And finding that optimal chunk size, it requires a lot of testing.
So what do people do in production?
In production, engineers often use a hybrid approach. They'll use the fast, cheap keyword search first to narrow down a huge library of documents, and then apply the more precise but more expensive embedding search on that smaller pool.
Okay, so we're shifting from just passive retrieval to active execution. The next step up is the agent architecture. This is where the AI moves beyond just summarizing things and actually starts to do tasks.
Yes. Agents perceive, they decide, they act, and they learn. They're really governed by the tools you give them. The core idea is that the AI model does the planning and the tools do the specialized work.
And what kind of tools are we talking about here?
Well, we can categorize them. You have knowledge augmentation tools like using a RAG or a web search. Then you have capability extension things like executing code, running a calculator, or accessing a translation API.
And then there are the high-stakes tools.
Right. Right actions. This is the ability to send an email, update a CRM record, or execute a financial transaction.
Wait, hold on. So the AI can actually hit send on a client email or modify a database. That raises the security and liability bar significantly, doesn't it?
It absolutely does. And that's why robust planning is so essential. For any complex multi-step task, the planning needs to be decoupled from the execution.
So what does that look like?
The agent first has to generate a plan. Then you need a step to validate the plan. That could be a human review or maybe another AI judge. Only then do you allow the final execution.
I noticed our sources were highlighting an open standard trying to manage all this complexity.
Yes, that's the Model Context Protocol, or MCP.
Yep.
It's an emerging standard that helps AI agents safely and consistently connect to tools and services.
Things like GitHub or Zapier.
Exactly, or your own internal systems. It basically standardizes how the agent communicates what it wants to do, making these real-world workflows a lot safer and more predictable.
Okay, but before we jump to the career roadmap, we have to talk about quality control. Evaluation and fine-tuning are really the unsung heroes of production AI engineering.
And evaluation is uniquely challenging for these models compared to, say, traditional software testing. Why is that?
Well, the tasks are just inherently complex and often really open-ended. You can't just check if the output is right when the correct answer could be 100 different versions of a poem, for instance.
Plus, the models are black boxes.
Right. We can only observe the output, not the internal reasoning.
When we talk about performance, the term perplexity comes up a lot. What is that?
So perplexity is a low-level metric. It measures the model's uncertainty when it's predicting the next token. A lower score is generally better during early training.
But it's not the whole story. No, not at all. Once you apply post-training, like supervised fine-tuning or RLHF, that's reinforcement, learning from human feedback perplexity becomes way less relevant to real-world performance.
But it's still useful for something, right?
It is. It's useful to detect if a piece of text was in the original training data. The model will have an unusually low perplexity score because it's not uncertain at all.
For an engineer, though, the ultimate metric has to be functional correctness.
Absolutely. Did the system actually do the thing it was supposed to do? Did the customer get the right flight booked? That's what the business cares about.
And to measure that at scale, teams are increasingly using AI judges.
Yes, using one very capable LLM to evaluate the output quality of another one.
But are these AI judges foolproof? I imagine they have their own issues.
Far from it. They're fast, they're cheap, and they often correlate well with human scores, but they definitely introduce new risks.
Yeah.
We know they're susceptible to biases like preferring the first answer they're shown, or favoring answers that are longer and more verbose.
So what's the engineering solution to that?
Robust testing and randomization. You always have to randomize the order of answers you show the judge to try and neutralize those positional biases.
And the final step is always connecting that evaluation metric back to the business's bottom line.
Yes, you have to. Your evaluation metrics have to connect to a clear business metric. For example, if you can prove that an increase in factual consistency from 80% to 90% lets you automate 20% more customer support tickets, that justifies the engineering investment.
So once your evaluation finds a problem, the AI engineer has to choose the right fix. Is it RGA, or do you need to go deeper and actually fine-tune the model?
This is the critical adaptation decision. And there's a pretty clear rule of thumb. If the model is failing because of a lack of information, it doesn't know your private data, it doesn't know about recent events, the answer is almost always RGA. Just give it the data it needs externally.
But if the failure is behavioral, what do you mean by that?
I mean, it consistently gives answers that are factually correct but totally irrelevant. Or it struggles to follow formatting rules like producing clean JSON. In that case, you need to adjust its core behavior, and that means fine-tuning. Now, since fully updating the weights of a giant foundation model is impossibly expensive, modern engineering uses parameter-efficient fine-tuning, or PFT, techniques.
And these let you update the model's behavior with a relatively small amount of data.
Yes, often just hundreds or a few thousand examples, while drastically cutting down the memory requirements.
And the undisputed leader in PFT right now seems to be LoRA, or low-rank adaptation.
LoRA is a really powerful efficiency technique. What it does is it freezes the vast majority of the original model's weights, and it only inserts and trains these small, lightweight, trainable components inside key layers of the model.
So by only updating those tiny components, you're saving a ton of memory and compute time.
A massive amount, while still successfully changing the model's behavior.
And to squeeze out even more efficiency, especially at inference time, we also saw a heavy emphasis on quantization.
Right. Quantization is all about memory optimization. It's the process of reducing the numerical precision of the model's weights.
So changing from a 32-bit number to a 16-bit number, for instance.
Exactly. This cuts memory cost, increases speed, and it's pretty much essential for running these huge systems efficiently in a production environment.
That brings us to the most practical takeaway, the career roadmap for you, the learner. How do all these concepts translate into the actual skills you need to land one of those jobs?
Well, our analysis shows a really clear three-phase path, and it's all built on technical mastery.
Okay, let's break it down. Phase 1. the essential foundations. You have to have production-level Python skills. That means you can build clean APIs, handle JSON, manage errors effectively.
Hmm.
Git and GitHub Mastery are just, they're non-negotiable. Your GitHub is your portfolio.
And you need the ML basics. You have to understand training, inference, and especially the mechanics of embeddings. Then comes phase 2, LLM integration. This is mastering the direct application of the models. You have to master prompt engineering and how to interact with the big proprietary APIs, like OpenAIs.
But you also need to know the open source options.
Critically, you have to be proficient with open source models, especially through Hugging Face. That's vital for any company with cost concerns or strict data privacy rules.
And finally, phase 3, building production systems. This is where the real value is. You need to master orchestration frameworks, especially LangChain, which is just the most popular way to connect models, tools, and multi-step logic right now.
Then you have to be able to design and implement a full RAG architecture. That means getting comfortable with vector databases like Pinecone or ChromaDB.
And last, you need the LLM ops skills.
That's right. Understanding prompt versioning, monitoring the model's performance, and crucially, rigorously managing your token costs in production.
So to prove all those skills, you need projects. Our sources suggest 3 really powerful portfolio project types that hiring managers are looking for.
The first is an AI decision support system. This would use RAG to ingest some dense documents and really focus on the output quality.
So structured summaries, risk indicators, and strong hallucination mitigation, like citing sources.
Exactly. The second is natural language analytics. This is all about connecting LLMs to structured databases using text-to-SQL. The project really needs to show you can handle robust schema reasoning and implement query safety protocols.
And the third, which is more advanced, is an AI workflow orchestrator.
This is where you use agents and tool calling to integrate with external APIs. Processing complex forms, applying business rules, and managing the audit trails across these multi-step processes. So what does this all mean for you? Modern AI engineering is, fundamentally, an integration and adaptation discipline. Those high salaries really reflect the scarcity of engineers who can move beyond just basic API calls and deploy these sophisticated, reliable systems using prompting, RA, PFT, and agents.
And it's interesting because the entire industry seems to be shifting its competitive focus based on this reality.
Absolutely. The whole field is moving from model-centric AI, where improvement just meant building a bigger model, to data-centric AI.
Where improvement means enhancing the quality of the data you use for adaptation and fine-tuning.
Exactly. High-quality, clean, consistent data is now the main competitive advantage because most teams have access to the same powerful foundation models.
That leads us to our final provocative thought. As you begin building, you should remember the principle that was emphasized throughout our sources. Complexity should serve a purpose.
Yes.
Don't just layer on agents or complex R methods or full fine-tuning onto your application just because you can. Start simple, test its reliability, and only increase the complexity of your system when it solves a real demonstrable problem for your application's performance or its reliability.
Then glean and build reliably messy later.